Hello, fellow tech enthusiasts. I would like to welcome you to our third course in the Zero to Hero series. Today, we will explore Docker. As part of the Zero to Hero course series, we aim to equip you with the knowledge needed to excel in your implementational use case, ace interviews, or tackle exam questions. If you have any doubts or if you believe we are overlooking any important concepts, please leave a comment on this video and we will address it. Part of housekeeping tasks. Who this course is for? This course is designed for anyone looking to level up their engineering skills. Whether you are seeking to refresh your knowledge or want to quickly learn Docker for any implementational use case or want to add a new tool to your resume, then you are in the right place. In terms of prerequisites, for the conceptual section, you don't need any prior knowledge of Docker as I will teach you everything. As this is a lab-based hands-on course, I want you to get some practical exposure. That is why I will encourage you to please follow with me. To perform the hands-on lab, you should have basic familiarities with Git, and if you want to perform the lab on Cloud VM, then you should have AWS or Azure free tier account. If you do not have, I would like to encourage you, please create one and then join me back. We can wait for you. Now let's get started with today's topic. We'll start with what is Docker, followed by what problem does it solve, and then how does it help. Before learning any new technology, you should know what is all about, what problem does it solve, and how that tool or technology will help. We will clarify all these questions before diving deep into today's topic. Then we'll move to section 2, where we are going to discuss Docker versus virtual machines. What are the similarities, what are the differences, and what are the advantages. Then we'll review Docker architecture. After that, we'll discuss Docker desktop. Then we'll move to section 3, where we'll install Docker. And this will be the practical section where you will follow all those labs with me. Then we'll create a Docker container. Although we'll use Docker images from Docker Hub, we'll create a custom Docker container because most of the time in your organizational use case, you need to create a custom Docker container. That is why you are going to put more focus on creating a custom Docker container. Then we'll run the Docker container. After that, we'll talk about the image version control. This is another one very important aspect. We already talked about create custom Docker image. Then we are going to review the necessary Docker commands. After that, we'll move to section 4, where we'll discuss offering from different cloud providers. No matter from which location or which organization you belong, your organization should be affiliated with any one of the cloud hyperscaler like either AWS or Azure or GCP, and I will help you to familiarize with all those services that is offered by the cloud providers. Then we will review the DevOps deployment process. This is another one important aspect that how Docker can help us in the development and the deployment process. Then we'll review the Docker orchestration and what are the tools or what are the platforms that is available for Docker orchestration. Then we'll move to more on the networking part. In section 5, we will review all the Docker networking options, then Docker load balancing, then dynamic port forwarding or dynamic port mapping. And at the end, I will give you Docker best practices. Throughout this course, we have used real-life examples, animations, and hands-on exercise to make this session effective, interactive, and easy to understand. If you encounter any error message or have trouble understanding a concept, please note down the timestamp and the error message and then leave a comment to this video. I will do my best to clarify your doubt and resolve your error scenario. Now we have a lot to cover today, So let's jump right into it. First, we'll try to understand what is container and why we need container with the help of a real life scenario. Let's assume Sarah is our friend and she is an IT professional working with some MNC. Now, currently, she is residing to an apartment to Mumbai. If she wants to relocate within the same city, maybe to a different apartment, normally what she will do? She will pack all her luggages, utensils, everything into car, and then she will relocate from apartment 1 to apartment 2. Yeah, I know there are different options. They can call packers and movers and all. But on a high level, that is the normal process or procedure when it's a small distance. Now let's assume Sarah is in Mumbai and now she got transferred to Bangalore. How she is going to relocate? If she is trying to use the previous approach, that is packing everything into that car, that might not work. During that process, it will break, it will not fit in the car. The option is she has to pack it properly, she has to box it, or she has to organize everything inside storage containers. That means organizing everything inside storage containers, it will make it portable. And with that, she will be able to ship it. Either it could be a packers and movers, or it could be her own car, or it could be with train, bus, whatever she wants. Now imagine if she is going to relocate to, let's say, Los Angeles, California. It's an overseas trip. If she wants to pack everything, obviously she needs a ship. Those cars, truck, that is not going to work. Now, if everything in container form, she will be able to easily port to the new location. The point what we are trying to understand from this example, if we pack everything to container, it become portable. It does not matter which form of transportation or what distance you are traveling, you will be able to organize and you can ship as is. Now with this example, with this concept, let's try to understand Docker. Like storage containers from our previous example, Docker containers are used to organize application and dependencies in a clean and methodical way. Let's review the application components that are required to run an application seamlessly, starting with servers, operating system platform, interface, runtime, configuration, dependencies, and many more. If any one of these components are missing, then the application will not work. The application deployment process may fail. Coming to Docker, it's an OS level virtualization technique to deliver software in packages called container. That means inside Docker container, we can package all the application components starting from source code, dependencies, configurations, runtimes, system tools, and then deliver to different environments. When we package the application as a Docker container, it becomes portable, easy to deploy, and we can run anywhere irrespective of the operating system and system architecture. That means it will deploy seamlessly in a ARM base or even in x86 base servers. Once we create the Docker image, we can store them for future use. And using a single Docker image, we can create as many containers as we want. The way we version control our source code, Docker allows us version control the images and also for future use and distribution. Don't worry, we will review all the components in great details. To summarize, Docker is a powerful tool to develop, deploy, and run applications more efficiently. While explaining the Docker concepts, I briefly touched on the topic of what problem Docker solves. In this section, we'll review the scenarios of application development and deployment processes before and after Docker. We will start with the application development process before Docker. To begin, we have a development team trying to build some application software. As a prerequisites, they have to install the runtime, dependencies, and other software components like databases, message brokers, etc. etc. A very common practice in every organization is that developers use Windows laptop while the production, stage and test servers run on Unix or Linux. As a result of the operating system variations, there are often differences in software version, binaries, and installation processes. After completing the prerequisites, development team have coded the application and some DB scripts. Once the development process is completed, the development team will perform unit testing. Then they will generate the artifacts along with the SOP or textual step-by-step guide on how to deploy the application to higher environments. And then the artifacts will be handed over to the deployment team. The deployment team will try to deploy the application artifacts to non-prod or production servers following the textual guide developed by the development team. They will use this guide to install dependencies, runtimes, or even create the configurations. Most of the time, we observe the deployment failed because of one or many reasons like library conflict, missing dependencies, missing steps, ambiguous instruction, or even missing components. This will trigger back and forth discussions between the development team and the deployment team. As a result, tedious triage sessions as debugging any issue in production or stage servers where the development team will not have access to validate configurations is difficult. As a result of that, we faced lengthier deployment process, long application outages, and last but not least, blame games between the teams. Now let's understand the new and improved process post Docker. With Docker, developers no longer need to request software or runtime installation on their local computers. As a result, there are no binaries, installers, OS dependent packages, or custom configurations. Instead, developers can pull the required software's Docker image from the public Docker Hub, where all images are stored and publicly available. If they need to use multiple softwares, then they can pull each one separately and run them as Docker containers. After the setup, developers modify the code, package the source code with all dependencies and required configurations, and create a custom Docker image. This custom Docker image is then pushed to the Docker Hub again, but this time to a private repository. Here comes the deployment team with servers. Instead of following textual SOPs for configurations and dependencies, they pull the custom Docker image from the Docker Hub and run it on the servers. As one-time prerequisite activity, Docker should be installed on those prod and non-prod servers. Apart from that, there will be no manual configuration, missing dependencies, library conflicts, or missing components. As a result, we see a shorter and error-free deployment process with less room for human error. I hope these examples clarify how Docker has improved and expedite the software development process. Let's review Docker versus virtual machines. While introducing Docker, I mentioned it is a virtualization technique. On the other hand, we have virtual machines. And you all are familiar with key players like VMware vSphere, Citrix, and Microsoft Hyper-V. So, why do we need another virtualization software? Moreover, Docker is very popular nowadays. What is the reason for this popularity? What are the differences between Docker and virtual machines? What are the advantages? We will answer all those questions in this section. To begin, let's understand computer architecture and how software and hardware interact. For a laptop, there are two main segments, hardware and the host operating system. The host OS could be Mac OS, Windows, or Linux. On top of this operating system layer, applications are running. Let's assume we have an application with Node.js version 20.11 and MongoDB 3.0 running inside our laptop. Now we have a requirement for a second Node.js application which will require Node.js version 21.5 and Mongo 4.0. Can we host two different versions of the same software on one laptop? The answer is no. Using conventional methods, we won't be able to host two different versions of Node.js or MongoDB on one laptop. Furthermore, it's not possible to directly install two operating systems on one laptop, which is very common use case for any organization. This scenario creates the foundation for virtualization. Coming to virtualization, servers have the same two layers, hardware and the operating system. However, virtualization adds an additional layer called hypervisor. A hypervisor is a software layer that enables multiple operating systems to run concurrently on a single physical hardware platform. It abstracts the physical hardware resources and allocates them to virtual machines. There are many hypervisors available in the market. vSphere from VMware, Citrix Hypervisor, and Hyper-V are the popular ones. Hyper-V is only for Windows, whereas the previous two are OS agnostic. With the help of this virtualization technique, we can now run two different operating systems or two different software versions on the same server. This is exactly what every organizations are doing in their data centers. But if we take a step further, because of the dedicated guest operating system in every virtual machine, it takes a good chunk of the host hardware. As a result, we can't run many VMs on one host. If we need hundreds of VMs, the infrastructure cost will escalate quickly. Moreover, smaller applications, there could be resource wastages. Now the question is, how can we run hundreds of applications concurrently on one server? The answer is Docker. Docker does not add a hypervisor layer. Rather, it adds a software layer called container engine on top of the host operating system. Docker containers run on top of the container engine layer. In contrast to a dedicated operating system for VMs, containers share the host operating system, which makes them lightweight. Because of their significantly smaller and portable nature, you can run hundreds of containers on a regular server node. Now, hypervisor or container is a topic that I can talk for hours. If you want to learn more about hypervisor, please drop your request as a comment to this video. We will talk about hypervisor in a dedicated session. Before we proceed further, I would like to request you, if you are new to our channel or haven't subscribed yet, then please consider subscribing to our channel and please click on the bell icon to get notification for any new topics. We upload new videos frequently. Let's continue with the session. In this segment of the video, we will review the difference between Docker and virtual machines. In the previous slide, we saw that the containers are lightweight and don't contain a full operating system copy. The average container size is in MBs. In contrast, due to the dedicated guest operating system copy, VMs takes up a lot of storage space. An average VM size will be several gigabytes. Containers start quickly in couple of seconds. In contrast, virtual machines require a comparatively longer start time. On average, under normal conditions, a VM can take a couple of minutes to start. Due to their portable and lightweight nature, containers consume fewer hardware resources, making it possible to launch hundreds of containers on an average server node. In comparison, VMs are resource intensive. Docker containers share the host operating system, whereas virtual machines support dedicated operating system we call guest OS. The only downside of Docker that I have observed is host exploits. As Docker shares the host operating system, any exposure or exploits to any one of the Docker containers can breach that specific container boundary and affect other containers and the shared hardware. This is not the case for virtual machines. VMs run in isolations as fully standalone systems, making them immune to any exploits from other virtual machines on the shared hardware. I hope now you have a clear understanding on the distinction between Docker and virtual machine as virtualization methods. In this section, we will dive deep into Docker architecture, which operates on a client-server model. Docker client is a command line interface or CLI tool, enables user to interact with the Docker host or server. We can use the CLI interface to run commands to build, run, and manage Docker containers. Zooming to Docker host, a crucial component is Docker daemon. Docker daemon is a background process responsible for executing user requests and managing Docker containers lifecycle. Another essential element on the Docker host is local images. Docker stores a copy of the Docker image to the server for future uses. Docker images are the read-only templates containing instructions to create Docker containers. The third block in the Docker architecture is Docker registry. This is a centralized repo to store all Docker images. When we refer a Docker image, the Docker daemon first checks its availability locally. If not found, it pulls the image from the Docker registry. We will review all these components and features in great details during hands-on labs. When we run a Docker image, it creates a Docker container, and you can employ a single Docker image to launch multiple Docker containers. In this architecture, we saw the Docker client is a CLI tool. But if you are a Windows user and don't like CLIs, then Docker has a solution for you. It's called Docker Desktop. When Docker initially launched Docker Desktop, it was only available for Windows and Mac operating systems. However, currently Docker Desktop is available even for Linux operating system as well. Docker Desktop provides a graphical user interface or GUI that makes it easy to manage containers, images, and volumes. During our hands-on, we'll download Docker Desktop from official Docker website and then review the installation steps. Docker Desktop is a full package of tools and it contains both GUI and the CLI options. Now let's understand why Docker Desktop was introduced for Mac and Windows operating systems. While discussing Docker versus virtual machines, we reviewed the hardware and the software layers of a server. If we zoom into the operating system layer, the operating system has built into two components, OS kernel and the OS process. The OS kernel or the operating system kernel is the core program of any operating system that controls everything in the system, such as running processes, managing hardware devices, and handling interrupts. It also serves as interface between the hardware and the processes of that computer. If we compare the system architecture of three most widely used operating systems like Linux, Windows, and Mac side by side, on a very high level, it looks like this. Every operating system has its own specific kernel, and that is the reason you cannot use an installer file built for Windows to install software in Mac and vice versa. When Docker was originally created, it was natively built for Linux. Since you cannot run any Linux-based application to Mac or Windows because of the OS kernel, Docker was not compatible for Windows and Mac initially. To solve that problem, Docker Desktop was introduced. Docker Desktop added a thin layer of hypervisor with a lightweight Linux distro or Linux distribution which provides the Linux kernel on top of Windows and Mac operating system kernel. Addition of this Linux kernel makes Linux containers compatible with Windows and Mac operating system. Now we have two options to access Docker. Either you can use Docker Desktop or Docker Engine. You can use any tool you like, but let's review them side by side. In terms of interface, Docker Engine is a CLI based tool, whereas Docker Desktop has both GUI and CLI options. The appropriate audience for Docker Engine should be developers and system administrators, whereas developers should use Docker Desktop. In terms of use case, Docker Engine is ideal for build, run, and manage Docker containers, whereas Docker Desktop is ideal for developing and running Docker containers. We will install both the tools in our next section, and I am very excited for the demo part which will come right after this slide. In this Docker installation demo, we will install both Docker Engine and Docker Desktop. I am on the official Docker documentation page. To access this page, you can type docs.docker.com into the address bar or search for Docker Desktop on Google. If you are using docs.docker.com, then you have to go to manuals, or else I can go to Google and search Docker Desktop. I'll skip the topmost search item because that is going to take me to www.docker.com. I'll come to the second item where I have docs.docker.com. And then I'll click Docker Docs from the left hand side. Manual. Here you go. I am in the dashboard from where I can download and install Docker Desktop. For this installation, I request you to please follow the steps provided in the documentation. As new Docker versions released frequently and the installation steps may change. If you notice any updates to the steps, don't worry. Once you complete them, Docker Desktop or Docker Engine will be installed on your laptop. Let's start with the Docker Desktop and install it on Mac OS first. I'll go to Docker Desktop. I'll scroll bottom of the page and then I have install Docker Desktop. Since I'm installing for Mac, I'll select the Mac option. If you are installing for Windows, select the Windows, and Linux if you are installing for a Linux. I'll go to Mac. First, I'll review the system requirements. That is very important. Mac has two different chips, one with Intel chip and second with Apple Silicon chip. Please select the tab which is applicable for you. I have a Mac with Intel chip, that is why I'll follow these steps. There is an important alert. It is saying Docker Desktop supports latest Mac version and the last two releases. That means if you are in Mac OS version 14, 13 and 12, then Docker Desktop is available for you. But if you are in an older version of Mac OS, such as Big Sur or Catalina, Docker Desktop may not be compatible for you. Additionally, there is one more system requirement, at least 4 GB of RAM. Please review both the requirements, no matter if you are using for Mac, Windows or Linux. Now let's review the system requirement for Windows. Here are the Windows system requirement. Before installing into Windows, please review those requirements properly, and similarly for Linux. You can see we have installation guide for Ubuntu, Debian and Fedora. You can use this set of instruction and you can install Docker Desktop there. Next, I'll go back to Mac again and I'll download the installer file and I'll install. I have Mac with Intel chip, that is why I'll click this button and it will start downloading the installer or the DMG file for me. See, the download has initiated. The installation process for Mac is very simple and easy. The Docker DMG file downloaded successfully. I will double click the file to open the installer. I'll drag the Docker icon into the application folder. The copy process is in progress. The copy process completed successfully. Either I can go to Launchpad and access the Docker icon, or I can go to application folder and then find the Docker icon and click. I am inside application folder. I'll click to open. I will accept the Docker subscription service agreement, and here you go. The Docker desktop has been installed and started successfully. The Docker installation process for macOS is so simple. Docker desktop also comes with the CLI option in addition to this GUI. You can use this graphical user interface to browse running containers. Currently, I don't have any containers running. That is why nothing is coming here. You can go to the image tab and also browse the available images. You can see I have some old images. Maybe I will clean all those images after this demo. To check if Docker is running, you can go to that top menu bar, and if you see this Docker icon here, that means Docker is currently running in your system. If you don't want the Docker to run, you can go ahead and kill that process. We have successfully downloaded and installed started Docker desktop for Mac OS. Now we'll install Docker Engine for Linux. The Docker documentation provides a step-by-step process for all popular Linux distributions. Here we have for Ubuntu, Debian, Fedora. However, this documentation does not cover installation on Amazon Linux or Amazon EC2 instances on Amazon Linux operating system. Since the steps for Amazon Linux or Amazon EC2 instances running on Amazon Linux are different, you may face some challenges here. If I go to Fedora, it has step-by-step process, and if you will follow those steps, you will be able to install for Fedora. But you can see for Amazon Linux 2 or Amazon Linux 2023, they do not have any instruction. As I promised at the beginning of the course, we will teach you everything you need for your specific use case right after this course. That is why we will show you the installation process for Amazon Linux. Now let's navigate to AWS Management Console and continue there. I have logged into AWS Management Console and I am at EC2 dashboard. I already have an EC2 Linux instance running in my account, which I have launched just before this demo. Let's review some attributes before login inside the EC2 instance. The name is Docker Demo. I'll select the instance, and if I'll go to details, this is a T2 micro instance. That means this instance will be covered by EC2 free tier. If you are following along with me, you won't pay anything to AWS in terms of AWS billing. Next, we'll review the platform, and the platform is Amazon Linux, and the AMI is Amazon Linux 2023. Currently, Amazon is promoting Amazon Linux 2023. They have another one Linux version, Amazon Linux 2 as well. To help you with this demo, I have also created this GitLab repo where I have provided all the commands and supporting artifacts we need for today's demo. I will provide the link of this repo in the video description. You can refer if you need to. Now I'll take you to the first file, install Docker Amazon EC2. I have given the name based on the purposes. I'll open the first file. Here I have listed all the commands that you need to install Docker in Amazon Linux 2 or Amazon Linux 2023. One point I'd like to highlight, here I have given steps both for Amazon Linux 2 and Amazon Linux 2023. Based on your AMI or based on your Linux version, please use that specific command. If you are using Amazon Linux 2023, please use this command. If you are using Amazon Linux 2, please using this command. But do not use both the commands. Now I'll close this GitLab repo. as I don't need. I'll try to connect to the EC2 instance using Instance Connect. I'll go to Connect, and from Instance Connect, I'll connect. I have logged into the EC2 instance. Now I'll try to check if Docker is available or not. I'll run Docker version. Command not found. That means Docker is not available in this EC2 instance. We have just launched this EC2 instance, and this is Amazon Linux 2023. Now let's try to install Docker in this EC2 instance. I'll start with sudo su such that every time I don't have to type sudo, I'll elevate my privilege. Next, I'll update. So I'll put yum update -y. This will update the install packages and package cache on this instance. Next, I'll install the most recent Docker Community Edition package, and I'll use yum install -y docker. The Docker installation process has started. It will take some time, maybe 30 to 35 seconds before it will complete. Docker has been successfully installed in my EC2 instance. Now next, we'll start the Docker service and we'll run service docker start. Yes, the Docker has been started. Next, again, we'll try to check the Docker version. Here you go. This time I can see a client section with version 24.0.5 and a server section with the same version. If you are not seeing both the section or both the components, client and the server, that means either your server has not been successfully started, or maybe your server or the Docker has some issue. Since we have installed Docker, next we'll try to pull some Docker image and we'll try to run as Docker container. Let me take you to Docker Hub. During those presentations, multiple times we talk about Docker Hub as the image repository. Now I am inside Docker Hub and I will try to search some image from here that we can run. We want to run a web application that we will look for Nginx, and I'll type Nginx. Okay, I have list of images for Nginx here. Now, if you concentrate on the left hand side, there are three different types of images. The top one is Docker official image. Docker official image refers to images that are curated and maintained directly by the Docker INC. These images are considered to be most reliable and trustworthy source for common use software such as databases, programming languages, and runtimes or any web servers. The next one is verified publishers. These images come from a trusted third-party publishers who has been verified by Docker INC. While they are not maintained by Docker INC directly, but still they are considered reliable. And the third part is sponsored OSS. That means Docker sponsored open source softwares. In most of the cases, some third-party providers, they will take the base image. On top of that, they will create some custom image and they will publish. For our demo, we'll stick to Docker official image. The top one is Nginx. I'll click to the Nginx. To pull the image, here is the command docker pull Nginx. And then there are different tags or different versions of the image available, and we can select any one. If we specify any version, then it will pull that specific version. If we do not specify any version, it will pull the latest version. Now let's try to pull one of the image version into our Docker environment and run there. I'll copy this command and I'll go back to my EC2 Instance Connect. I'll clean the screen and then I'll paste the command. I want to pull a specific image version. That is why I'll go back to Docker registry or Docker Hub, and I want to pull 1.25.3. Now it is pulling that image from that Docker Hub and it will download the image into this local system. One point, if you observe, we have only used the command docker pull and then the image name and the tag or the version without specifying any address. Docker engine in my system has connection established with the Docker hub and it knows from where to pull the image. That is why we do not have to specify any address here. If we put Docker pull, the image name and the specific tag you want to pull. Next, we'll try to list all the images that is available in my system. It should have only one. And to do that, I'll type Docker images. Sorry, I have misspelled the Docker spelling. Here you go. I have only one image that I have downloaded recently. There is one more command you can use for the same purpose, and that will be docker image ls. I'll make sure every spelling is correct. Yes. You can see both the command docker images or docker image ls will give me the same result. Next, we'll try to pull without specifying any version number. This time, I'll remove the tag or the version number and I'll pull. You can see pulling using default tag as latest. That means if you are not providing any tag, it will pull the latest and it is pulling from library Nginx. So the pull is successful and it has pulled from docker.io library. Now let's execute the list image command again. I have two images that I have downloaded, Nginx 1.25.3 and Nginx latest. Now let's try to run this image and create a container. Okay, before even doing that, let me show you one more command. I'll execute docker ps and this will list all the containers that is running in my system. Currently, I do not have a running container. That is why it is not showing anything. Now let's run the first container. For that, I will use docker run and then I'll use the Nginx 1.253. Okay, the Docker container has been launched successfully and it is running. Now, since the Docker container is running and it has all those logs, it captured my console. I won't be able to type anything and I'll show you the exact process, what you should do. But before that, let me launch one more session and we will execute the command there. I'll select the EC2. Again, I'll go to connect and I'll use instance connect. I'll elevate my privilege and then I'll run docker ps. Here you go. You can see I have one Docker container with the container ID that is running and the image is Nginx 1.25.3. Now, if I'll go back to my previous console and if I press Ctrl C, then the process will exit and it will stop the container. Now, if I'll run docker ps again, there is no more container. Now I'll go back to my previous console and this time we'll run the EC2 container in detach mode such that it will not capture my console. And for that, I'll use docker run -d, that is for the detach mode. And then I'll use Nginx 1.2.5. Here you go. This time the container is running, but I have access to my console. And if I execute that command, docker ps, I'll be able to see this container is running again. Now what we can do, we can run one more container or we can execute the same command again. Okay, so it has launched another one container. Now let's run the docker ps again. You can see I have two containers with different container ID and both are running Nginx 1.25.3 and one is started very recently and one it's already running. Similarly, I can run one more container and I can run docker ps. If you remember, multiple times I told during the presentation, using one single Docker image, we can run multiple containers or as many containers as we want. Now let's kill one of the container. And for that, we will use Docker rm. And I want to kill with force. That is why I will use -f. And then I'll take this container ID. Okay. Now let's again run the docker ps command. This time I have only two containers. That means I have successfully killed or removed one container. By this way, you will be able to launch multiple containers, you will be able to remove containers, you will be able to kill containers. Now, one more point I would like to show you. This time, again, I'll go back to Nginx, and instead of 1.25.3, I want to download, let's say 1.24.0, and I want to run one container using this image. This time, what I'm going to do, instead of downloading that image, I'll directly run using that run command. So I'll give docker run -d and nginx 1.24.0. I'll verify the version number again, 1.24.0. I'll correct the Nginx spelling. Now you can see unable to find the image locally. Whenever we'll run a Docker image, first it will try to find out in the local image storage. If the local image is not available, then it will pull from the Docker IO or the Docker Hub, and that is exactly what it is doing. And since the image was not available locally, that is why it pulled from the Docker Hub and then it ran. Now my container is running. Previously, I had two containers and both with 1.25.3. Now, if I will run Docker PS, I should see three containers. And exactly what I am seeing, Nginx 1.24.0 and 1.25.3. Now let's do one more thing. We'll run docker run, and this time we'll not specify any tag or image version. What it is going to do, it is going to run the latest image. Okay, and we'll execute docker ps. Now I have four containers, one with the latest version, one with 24, and two with 1.25. Now let me kill those containers because I do not need those containers. Next, I am going to show you or demonstrate you how to create a custom container. And that will be more important for you because in all your implementational use cases, you have to create your own custom Docker container. And this process is very important, and we should understand how we can create the Docker file and how we can create the Docker image, and then how we can push the Docker image to Docker Hub. Let me kill all those containers first. I have killed all the four containers. Now, if I'll run docker ps, it should not show any containers are running. Yes, there is no more container. Now, let me show you one more step. This time we'll list all the Docker images. Here I have three images. And next, maybe I'll try to remove the latest image. I'll use docker image rm, and I want to use force option -f. And I will take this image ID and paste here. Okay. So it has untagged first, whatever the container or wherever it was tagged, first it's untagged and then deleted. Now, if I'll run again the docker images command or list command, I have only one image or the 1.24 because 1.25.3, that was the latest image. That is why it has untagged from both the places. And I have only one image now. Now, the next step is we'll create a custom container. To create custom container, first we'll create a directory where we'll put some of the web components because we want to create a simple JavaScript application. And again, to perform this step, you don't have to be expert in JavaScript or you do not have to know all those JavaScripts. We are going to create a very simple JavaScript application. Let's create a directory first, and I'll give a name simple JS app. Okay. Now I'll go inside that directory. The first thing, we are going to create a JavaScript file inside that. I'll type bhai and maybe I'll put app.js. Now I'll insert some command here and I am going to write a very simple command, that is console.log, and I want to print something on the console, and that will be my JavaScript application. So I'll start with console.log and I'll type some message like hello from Cloud Expert Solution Docker demo. Okay. So this is my JavaScript file. I'll save and I'll exit. Next step, I have to create a Docker file. And if you remember, while we are discussing about the Docker steps, first you have to create a Docker file. When you will build the Docker file, it will create a Docker image. And when you will run the Docker image, it will create a container. Now to create the Docker file, again, I'll use y and I'll put the name as Docker file. Please remember this naming syntax. You have to use capital D for the Docker and file is small without any extension. So Docker file will not have any extension. It will have a name, starts with a capital letter and then the Docker file. Inside the Docker file, we have to write some steps. Since this is a Node.js application, we need a runtime, right? That is why we'll first start with or we'll provide a runtime. But before that, let me take you to Docker Hub and this time I'll show you Node Alpine. I'll use Docker official image and Alpine is a Linux distribution that is a very thin or very small Linux distribution. And if I'll go back, you can see the size is only 5 MB. And we are going to use this Alpine and there are different versions available and we are going to use LTS version of Alpine. So I'll go back to my EC2 management console. I may close this one. I'll insert. First, I'll start from, that means I'm going to take, and what I'm going to take, since this is a Node.js application, I need Node and then the version, and the version is LTS Alpine. When I'll run this Docker file, it will fetch that Node Alpine for the runtime. Then I'll copy all the files, whatever we have inside that application folder or whatever we have created for the web application. For our case, it is only one file, but for your implementation case, it may have more than one file. So that is why we'll copy everything from the current directory to a directory called app. Next, we have to execute a command. If you remember that when you are executing a Node.js application, you have to write npm node and all those stuff. So that is why we have to start that node. And this time we'll use cmd node and then the file name, whatever the file, the Node.js file we have. And we have that file app.js that is inside my app folder. So app/app.js. Now for my case, it may not make much sense that I have only one directory structure, but sometimes you may have to repeat this /app or the directory structure in multiple steps. If you have such kind of use case, instead of repeating that /app or the directory, every time what you can do, you can set up a work directory and we'll exactly do that. We'll create a work directory, work dir, and there we are going to give the path as app. When I set that work directory, I do not have to use the /app multiple times going forward in all other steps. So that was all. As I mentioned, it will be a very simple application or simple Node.js application. First, I have fetched that runtime from Docker. Then I have copied all those source code into a app folder and then I'll run that application. Now let me save and quit from here. Okay. So if I'll do ls, I should see I have one app.js file and I have a Docker file created here. The next step would be I have to use this Docker file and I have to build the Docker image. For that, I am going to use Docker, then build I have to specify a tag name. If you remember, in Docker Hub, every image is maintained using a tag or image version. That is why I will also use a tag, and maybe I'll give tag as app.1.0, and that is the tag I'm going to use. Sorry, I have missed one part of the command here where the image will be created, that I have to specify. I will not delete this part of the video such that you will also not make that mistake, or you will also not face that issue that why that error is coming and you are not able to understand. So I have to add one dot. That means I want to create that image in the current directory. Now the image is getting created. Okay, the image has been created. Now if I'll execute the command docker images, I should see two images, one the Nginx and the second the custom image that we have created. Next, we'll try to run this custom image, because once you will create that custom image, you will try to validate, right? So for that, we'll use docker run and then the tag name. For our case, the tag is app 1.0. Okay. Now my container is running. I can see that hello from Cloud Expert Solution Docker demo. That is what exactly I did. I wrote this message in app.js file. Next, we'll try to push the image to Docker Hub. And to push the image to Docker Hub, we have to log in to Docker Hub. To log in, we will use docker login. Once I'll execute this command, it will ask for the login credential, that is my email ID or mobile number, whatever I have used, and the password. If you already have a Docker Hub login, you can use the login credential. If you do not have a login, now let's move to Docker Hub again, and it is time for you to create one login credential. For this login or for this account, you do not have to use your credit card or no price is required. It's a simple free login. You can go ahead and sign in to Docker Hub. Once you have completed sign in and logged into Docker Hub with your credential, you can come to repositories. I already have a repository created. If you do not have an existing repo, you can create one, and to create one repo, you have to click on the create repository button. The process is very simple. You have to provide a name. Maybe I'll use Docker demo repo, and you have to provide a description. Then what would be the visibility? As the name suggests, public will be visible to everyone and private will be visible only to you. So based on your requirement, select any one. I am not going to create a new one because I already have a public repo. So I'll cancel from this step. But for you, select any one visibility and click create. It will create a Docker repo for you. Now for my Docker Hub repo, this is the name. I have Cloud Expert Solutions / CES Docker repo. And I have to use the same Docker repo name whenever I'll try to push. But before that, let me pause the video here. I'll log into Docker repo. I'll clear the screen or clear all those logs such that I don't want to expose the email ID or the login credential. Then I'll come back. I have successfully logged into the Docker Hub, and then I have cleaned the screen. Now let's try to create, or let's try to push that image to Docker Hub. So first I'll create a local tag, and for that I'll use docker tag. And okay, before that, let me list the image such that I'll have the Docker image tag with me, and I'll use docker images. Okay. Now let's try to create a tag, docker tag. And for me, my image name is app.1.0. And then I'll use this repo name, the Cloud Expert Solution, this repo where I want to push in the Docker Hub. I'll copy that repo name from there and I'll paste. Next, I'll put a colon and I'll give the tag name or the version name that I want to push to the Docker Hub. Maybe I'll use the same tag name, app 1.0. If we'll again execute the command docker images, you can see that now I have three images, right? This one is for the Cloud Expert Solution CS Docker repo, and their repo, that image I am going to push to my Docker Hub. And as I mentioned, I am using the same public repo, but for your case, it will be private repo, but the process is same. Next, I have to push that image, and I'll use Docker push, then the repo name. And for my case, I'll copy the repo from here, followed by the tag name. And the tag is app.1.0. Now it is pushing that image to Docker Hub. The image has been successfully pushed to Docker Hub. We can go to Docker Hub and we can validate. Now if I'll refresh, okay, I should see that app.1.0, this custom image is available in Docker Hub, and it is available. Push date is a few seconds ago, and that is what we have done. Now, this is the way for your organizational use case. You will pull some runtime, you will build your application on top of that, then you will create the Docker file, then you will build the Docker file to create the Docker image. You will push the Docker image to Docker Hub in your private repo, but before that, you will obviously perform all the testing. Before we move away from this, let's review some important Docker comments. In terms of important Docker comments, we have already seen this list of available local images. We have already used both these. Then to pull specific image version, we have already seen pull latest image. We have already did the demo. Run a Docker image with specific version. We have already completed. List the running container Docker PS. Multiple times we have executed this command. Run a Docker container without a tag. That means you are running the latest one. Run a Docker container without the log. We have already seen the demo that in the detach mode, because when you are running the Docker container, the Nginx container, when you ran, it captured my console. And if you want to perform any other command, you won't be able to do. Now, in the detach mode, we were able to gain control, but there was no logs. There will be scenarios where you may have to see the container logs because of the debug purposes. Now, let's see how can you view those logs, and rest all the commands we have already visited or we have already practiced. So this one command is remained, that access container log, and let's try to access the container log first. I'm back to my EC2 console. Now I'll list all the images first. I'll put Docker images, and maybe I'll run the Nginx container again. And this time I'll use Docker run in the detach mode, that is a -d, then Nginx 1.24.0. Okay, the container is running, it is in detach mode, and now I want to access the logs. To access the log, first I need the container ID. So I'll execute Docker PS. It will give me the details about all the running containers. And now next we'll use Docker logs with the container ID. Now it gave me all those logs from that container, and since this is a very simple application, that is why it might not have anything, but when you will run your custom container, that time you might need this log to view or for debug purposes. So that was all those important commands that you should know by heart. And as I mentioned, I have that GitLab repo where I have listed all those commands. So you should not face any challenge to access those commands or to practice. Now let's continue to the remaining section of this session. Now let's review some important Docker commands in the development process flow. As one-time activity, developer will install Docker into his or her workstation. Next, they will complete the app development and will create a Docker file. Then the developer will initiate a build. Based on the specifications, a Docker image will be created. In this process, developer will use Docker build command and will specify an image tag name. This will be the custom Docker image, and user can provide a name that he or she wants. Once the Docker image created, to test the functionality, the developer will run the Docker image, which will generate a custom Docker container. The developer will use docker run command with the image tag specified in the previous step. As a next step, the developer will push the Docker image to a private Docker repo. The command is docker push and then the repo :image tag. That's the development side of the process. The next leg of the process is deployment, where system administrator will come into picture. The system admin team will pull the custom Docker image from the private Docker repo using the image tag. This will download the image to the server's local storage. Next, the system administrator will run the Docker image again, the same run command what developer used. A new Docker container with all application changes will be created and will run in the server. End users of this application will be able to access the app via internet or intranet. If you still have any doubts regarding the Docker basic concepts, please drop your questions as comment to this video. I want you to know this end-to-end process by heart. You will need these commands or steps at every stage when you work with Docker. We took the term Docker registry multiple times in our previous sections. Now let's dive deep into Docker registry. Docker registry is a central repo where images or container images are stored. One important point I want to reiterate: Docker registry stores the Docker images, not Docker containers. Docker registry allows you to pull pre-built images or push custom images. We have already reviewed couple of times. We need to use docker push command to push any Docker images to Docker Hub, or docker pull command to pull any images from Docker Hub. We also saw during our demo, Docker Hub allows us to create either a private Docker repo or a public Docker repo. And if you are thinking, is Docker Hub is the only option for us to store the Docker images? The answer is no. Now let's review some very popular public and private Docker registries. Docker Hub is the most popular choice for public container registry. Most of the services we are going to discuss provides option to host a private and a public repo. But we will only talk about the popular choices that organizations are using. Like Docker Hub has both public and private options, but organizations nowadays look Docker Hub more like a public container registry option. If you have a different observation, please let us know your observation as comment to this video. Under private, we have two options, either cloud native or cloud agnostic. We'll start with the cloud native options. Starting with AWS, AWS provides ECR and ECR store ECS, EKS and AWS Lambda as code containers. Next is Azure. The option is Azure Container Registry. Azure Container Registry supports for Docker, OCI images and Helm charts. Now OCI is Open Container Initiative and alternative of Docker, and Helm charts helps you to manage Kubernetes application. Now Google or the GCP has the service name Google Container Registry. Next, cloud agnostic. Under cloud agnostic, the popular choice is Harbor. Harbor is an open source private registry and Harbor provides granular access control. Next, JFrog. JFrog supports Docker images and Helm charts. Then there are two more options as cloud agnostic. One is Red Hat QA and GitLab Container Registry. Nowadays, GitLab is gaining popularity for both code repo and container repo. There is a third option and you can create your local Docker registry. You may not come across an use case where you need to host a local Docker registry, and it's not very popular option. However, it's important for you to know that there is an option to host a Docker registry locally. To create the local Docker registry, first pull the Docker registry image from Docker Hub and then run the Docker registry image in detach mode. That's why we have the -d argument here. If you remember, we have demonstrated this part during our demo. The next block in this command is 5000:5000, and this is a port mapping between the host port and the container port. We have a dedicated slide or section for that. We'll discuss in depth. Now when you will run this command, Docker will create a Docker registry container with the name my local registry. Next, we are going to review Docker image version control. This was the snippet of our Docker file that we have used to create our Docker image, and we have used LTS or long-term support version of Node Alpine. In some of the Docker files, you may see no version tag or maybe the latest tag. Using latest version for any packages is not a Docker best practice and not recommended for critical applications. Now on the other hand, Docker images are immutable. That means once you create a Docker image, you won't be able to edit or update that image. However, you can create a new version of that image. There is also a Docker best practice that says you should regularly update the base image and dependencies to patch vulnerabilities. Let's take an example. Let's say you are using Mongo 3.x version as your base image and you have created your custom image as 3.1.0. Software providers regularly update their products, and as part of the feature upgrades, Mongo released a stable version of version 4.x.x and so on. I mentioned that once you create a Docker image, you won't be able to edit that image. Then how are you going to upgrade your custom image and keep it updated with the base image version? The answer is version control. When there will be a new stable version of the base image available, you should update your Docker file, rebuild the Docker file, and create a new version of the Docker image. Run the new image to update your containers and then push the new image to your image registry. There are multiple options you can use to maintain the image versioning. Using the image tag or the version number is one of them. Now, if you have an use case to show the version number in your application code, then instead of hard coding the version number, create a version file only with the version number. So it will be only one file and that will have only one line, the version number, and put it as part of your code artifacts. You can increment the version number as part of your Docker build. You will have some script which will read the version from the version file and increment it, and then let your application read the version number from the version file to display in the application. In this section, we will explore Docker offerings from various cloud hyperscalers. In your implementational use cases, you will often need to work with one of the three major cloud hyperscalers. Therefore, it is crucial to have a high-level understanding of their Docker offering details. We have already reviewed the Docker registry offerings from the hyperscalers. Now let's see what are the options we have to run Docker containers as part of our cloud workloads. The most basic option is to provision a virtual machine in your account, such as an EC2 instance or an Azure VM or a Google Compute Engine, and install Docker to manage containers and the environment, similar to what we did in our hands-on lab. However, this approach requires a significant amount of manual work and heavy lifting. Cloud hyperscalers take this burden by offering managed service offerings, allowing you to focus on your workload rather than managing the infrastructure and all other components. In terms of managed service offerings, AWS offers ECS or Elastic Container Service. If you want to run Kubernetes containers, then AWS offers EKS or Elastic Kubernetes Services. In both the cases, you have to manage the node or the host. But if you don't want to manage any infrastructure or even the scaling part, then you can use AWS serverless offerings called Fargate. You can run both ECS and EKS containers in Fargate. Other offerings are App Runner. If you want to quickly run and manage containers, then App Runner is the option. Nowadays, Lambda also supports container. That means you can run Lambda code as containers. If you like CLI based tool, then the option is AWS Copilot. You can use Copilot to build, release and operate production ready containerized application on Amazon ECS or AWS Fargate. Moving to Azure, Azure Container Registry, then Azure Container App, then Azure Web App for container. If you want to manage Kubernetes workload, then Azure offers Azure Kubernetes Services, and also Azure has an offering called Azure Service Fabric. Next, GCP. For Kubernetes workload, Google provides a fully managed offering called Google Kubernetes Engine. And also, if you want to go for serverless option, then Cloud Run. This was all the container runtime services from cloud hyperscalers as of today. But if your workload is in on-premises data center, then you can use on-premises VM to host the Docker workload. In this section, we will discuss Docker DevOps process and we will review how we can integrate Docker and DevOps together and automate the repetitive manual tasks. We will first review the end-to-end Docker DevOps process using popular open source options and offerings. Then we will pick AWS as the cloud provider and review using AWS DevOps how we can automate the process. If you are eager to learn DevOps, Azure DevOps and AWS DevOps are next in our pipeline. Be sure to subscribe to our channel and turn on notifications to receive an alert as soon as we will upload these courses. To start with, here is our developer with the required tech stack for the application development. Step 1. Developer will pull the Docker image for the database and the required runtimes. After completing the development, the developer will push the artifacts such as source code and configuration to the code repo. Let's assume GitLab here. At GitLab push event, that means when the source code will be pushed to GitLab, GitLab will trigger a Jenkins build. Jenkins is an open source build and deployment tool. Next, Jenkins will fetch and build the source code and will create a Docker image as the build artifact. After build, Jenkins will push the Docker image to Docker Hub but to a private repo. Jenkins will then trigger the deployment process for the servers and first pull the Docker image from the private Docker registry to the server. Then Jenkins will run the Docker image inside the server and the application will be deployed as a container. You may have automated or manual testing stages in between, and the automated test scripts can be integrated in this Jenkins CI/CD pipeline. Now let's review the same process using AWS DevOps tools. Step 1 is same. The developer will pull the Docker image for the database and the required runtimes. Step 2. After development, the developer will push the code to AWS Code Commit instead of GitLab. Code Commit trigger will automatically invoke build using AWS Code Build. Code Build will compile the source code and will create the Docker image. Instead of using Docker Hub, we can use ECR as image repo, and Code Build will push the Docker image to ECR. The AWS Code Build will then trigger the deployment process using Code Deploy. Code deploy will deploy the application in ECS or AWS Fargate. First, it will pull the Docker image from ECR and then run the Docker image to deploy the application as container. For the entire CI/CD orchestration process, we can utilize AWS Code Pipeline. You have the option to manually set up the pipeline or use infrastructure as code to create it. If you are interested in learning infrastructure as code using Terraform, we have a Zero to Hero course covering everything about Terraform. You can find that course on our YouTube channel. In this section, we will review Docker orchestration process. Let's consider a scenario where we have 3 Docker images, one for Node.js, one for Redis as a cache layer, and the last one for PostgreSQL as database. We are utilizing either a VM-based or a ECS service to manage the Docker containers, where we must handle auto-scaling and high availability aspects. When the application started, a single instance of each container is running on the node. Additionally, we have an application load balancer in place to distribute the loads. Container autoscaling is also configured to dynamically adjust the container counts based on application load. Suddenly, the node layer experiences heavy traffic. Due to container autoscaling, an additional Node.js container is launched. But that was insufficient. Consequently, a second additional node container is launched. Currently, the host is working with full capacity. Now the application started receiving heavy DB workload, which requires an additional PostgreSQL container to be launched. But the host is already full and there is no capacity left to launch an additional container. To launch any new container from my current state, we need autoscaling at the host level. One point we must understand here, autoscaling at container level does not automatically scale the host node, or container autoscaling is not equivalent to host autoscaling. We must create another node to place the new containers. This was only a part of the puzzle. Unlike serverless options to run a container, we must take care the configuration, provisioning, resource allocation, availability, load balancing, scaling, health monitoring, security, and many more. These are all manual tasks. Now imagine the task volume for big organizations who runs thousands of containers daily. Can you imagine how tedious that task could be? Then what is the option? The answer is Docker orchestration platforms. Docker orchestration platforms replaces the manual step with automation. Here are 2 popular choices, Kubernetes and OpenShift. Kubernetes is originally developed by Google, but it's an open source container orchestration platform and you can use across hyperscaler. No matter if you are in AWS, Azure, GCP, you have Kubernetes, and we already reviewed the Kubernetes management services as well. Docker networking is a very important Docker aspect, and you will find a very limited use case where you will get an opportunity to run Docker containers in isolation. Most of the time, you must establish connection or publish your Docker containers to outside world. Let's dive deep into the Docker networking domain now. Docker networking refers to the ability of containers to connect and communicate with each other or to non-Docker workloads. It's a virtual network created by Docker for all the containers. Docker containers have networking enabled by default, and they can make outgoing connections. However, a container has no information about what kind of network it's attached to, or whether their peers are also Docker workload or not. That is why we will focus more on the ingress part of networking. Let's assume we have 3 Docker images, one for Node.js, one for Redis, and the last one for PostgreSQL as a database. We are utilizing either a VM based or ECS service to manage the Docker containers. Our application containers are running in both production and non-production servers. As the container networking enabled by default, Docker containers located in the same node will be able to connect with each other. In our example, the Node.js container and PostgreSQL container can establish connection by default. But if you want the internet traffic to reach to your container, or if you want to establish communication from the Node.js container in production region to PostgreSQL container in non-production region in our example, that is not possible unless you configure the networking settings for the containers. So the container default networking will not support your implementational use cases. Then what are the networking modes or settings Docker supports? They are host, bridge, none, then we have IP VLAN and MAC VLAN. Now let's understand the networking modes together. We will begin with host networking mode, and we will use our previous example where we host Docker containers on a VM based host. Let's assume the host IP is 172.33.95.114. The host will have a port referred to as the host port, as this port is attached to the host. Every container will have a port called container port. Under host networking mode, containers share the host networking configuration. This means each container will not have a dedicated IP address. Instead, every container on that host will share the host IP, and the container port will be same as host port. In our example, every container will have the IP address as 172.33.95.114 and the port same as the host port. To access the PostgreSQL database, we need port 5432. When any request from internet will come to the host at port 5432 with the TCP protocol, since the container is using the host IP and port, the request will be directly routed to the container. Now let's understand what is the limitation of this network mode. We want our application to dynamically adjust the containers count based on the load, and we have auto-scaling setup for the containers. As part of the auto-scaling, let's assume another one PostgreSQL container has been launched. For the second container also, the IP address will be 172.33.95.114 and it will share the same host port. As a result of this IP and port sharing, ingress traffic for the second container will not be able to reach because the host port is already in use. That is why host mode is very simple. No configuration is required, but the problem is you can't use this mode when you have container auto scaling configured. Please remember this phrase: host mode is not applicable for horizontal auto scaling. Then what is the alternative? A better alternative of host networking is bridge networking mode. For bridge networking, we'll take the same VM based host example and we'll run two containers. In bridge mode, we create a new network bridge which allocates each container a dedicated private IP address. For our example in bridge mode, let's assume container 1, the bottom container, gets 10.100.75.135. and the container 2 gets 10.100.72.130. Again, these containers IP address are not public IP and internet traffic won't be able to directly reach to the containers. But the benefit of this dedicated private IP is now each container can use the host port in parallel. Since the containers are in the same host, by default they can communicate with each other. And both are using port 5432. To communicate with the outside world, we must publish these containers with port mapping. That is why we have to publish the binding between host port and the container port in this special format: curly braces host port colon curly braces container port. When you will see two ports separated with a colon, that means it's a bridge networking. If you remember, when we discussed local Docker registry, we used this terminology. Now, when the internet traffic is coming in port 5432:5432, as every container will have own private IP, the network bridge will route the traffic to container 1. For the second container, we won't be able to use the port 5432 as host port in the port mapping because the port is already used. We will use 5433 as host port. That means host port will be dynamic and it will be assigned based on the container launch sequence. Using this mode, we can use horizontal scaling and route traffic to the containers running in parallel. This resolves the first problem. However, introducing a new problem. Let's understand the problem first, then we'll discuss the solution. For easy understanding, let's take a simple version of the same diagram. We have both the PostgreSQL containers. The yellow box denotes the container port and the purple box represents the host port. To expose the containers externally, we are performing port binding. That means we are mapping the container port with a host port. The host port is not static. Rather, Docker dynamically assigns a port to each container based on the container launch sequence. Let's assume that the PostgreSQL container is getting used heavily and we need one more new host. The container port, which is static, will not be exposed to the outside world. Rather, the host port will be referred by the external applications to reach the container inside the host. And if that port is dynamic, then how are you going to get the host port beforehand and communicate the host port to other applications? Because you will not get the dynamic host port until the container will be launched. This can cause issue when you have multiple containers needing to expose the same port. You must be thinking, do I have to hardcode the host port and the port binding in the Docker file? The answer is no. You really don't have to hardcode any port or port mapping. When you will create the container task definition, you just specify the container port and set the host port as 0. That means for PostgreSQL DB, you will specify 5432. For HTTP application, you will specify 80. For HTTPS, you will specify 443 and so on. When the container will be launched, it will be taken care by the port mapping. Now the next question is, how will I get that port and how will be able to distribute the load when I have more than one containers using the same port? To answer this question, I'll use an AWS service. Other cloud providers also have the same capability. AWS Application Load Balancer is the answer for this scenario. AWS Application Load Balancer has the capability of dynamic port forwarding. Once the request will come to Application Load Balancer, the ALB will forward the traffic to dynamic ports. But if you will hardcode the mapping, then ALB won't be able to distribute the traffic to those ports. We already discussed the host networking mode and bridge networking mode. Now let's review the other part. Moving to none mode, as the name suggests, there will be no networking and containers will be isolated and will not communicate with external network. In all the previous network mode, we have discussed IPv4 network address. If you have a requirement to use IPv6 address as well, then you can use a network interface with the containers. Using the network interface, you can gain full control over IPv4 and IPv6 addressing of your container. On the other hand, if you want to assign a dedicated MAC address, then you can use MAC VLAN. So IP VLAN provides full control over IPv4 and IPv6 address, whereas MAC VLAN provides a dedicated MAC address. Before I conclude, like all other Zero to Hero videos, I want to share the Docker best practices that you must follow for all your use cases. To start with, please use .docker ignore file to exclude unnecessary files from your Docker context. This will reduce the build time and the image size. .docker ignore file is similar to .git ignore file for Git. If you are familiar with Git, then you should know .git ignore file. Next, use lightweight base image. If you remember, during the custom container demo, we used Node.js Alpine, which was about 5 MB size. If you are using a jumbo base image, then your custom image size will grow unnecessarily. Third, minimize the number of layers. If you remember, in our Docker file, we have used run, copy and all those sections. Each run, copy will create an additional layer. If you are using multiple run blocks, try to combine steps from layers to a single layer. Then use specific image tags. When you are pulling image from Docker, please try to avoid using latest or tagless image pool. And please do not use latest version for production or critical application workload, as latest version can have non-remediated vulnerabilities. Next, keep your container stateless. Then use environmental variable for configurations. If you have region specific configurations, then instead of hard coding the values, please use environmental variable or parameters from parameter stores. Again, please do not hard code any configuration. Next, don't run process using root login. This is a very important security best practice. Instead of using root login, create a user with required privileges. Then use multi-stage builds. Multi-stage builds will help you to drastically reduce the size of your Docker image. Then next, keep images up to date. We discussed this during image versioning. Regularly update the base image and dependencies to patch vulnerabilities. And use base image only from the trusted sources. We discussed 3 different image sources if you remember: Docker official image versus verified publishers versus sponsored OSS. And last but not least, manage secrets securely. Instead of hard coding passwords, API keys or any sensitive information, please use Docker secrets or cloud specific services like AWS offer secrets manager. So please do not hard code any secrets in your Docker container code or application code. That concludes our session for today. I understand it was a lengthy video, but our aim was to cover all the necessary details thoroughly so that after this session you feel confident to implement Docker in your real life use cases. I believe after completing this course, you will feel more comfortable and confident working with Docker. And you can proudly say that now you have a solid understanding of Docker. If you like our effort, Please give us a thumbs up and please share this video with your friends and families. Subscribe to our channel and please click on the bell icon for more content like this. Thank you for watching.